For our first example using cyclotron, we're going to talk about making a magnetron. So what's a magnetron? A magnetron is basically a device that creates a uniform magnetic field that you can use in an electronic circuit, for example, to let electrons move in the uniform magnetic field. So why would we even want such a thing? Well, this actually goes back to World War II when they were deploying the first radar technology. And so in order to do radar, they needed to have radio waves, frequency about 750 millihertz. Now we currently use way more than 750 millihertz for radar, but in those days that was closer to what they were using for some types of radar. The problem was making radiation of that frequency because that was way too fast for the electronics to be able to produce 750 megahertz. They had no way of doing that with the electronics of the day. And so the idea they came up with was to have electrons that move around in circles with a frequency of 750 megahertz. So how do you do that? Well, if you remember, when we started talking about this, we talked about cyclotron motion, in which if you have a magnetic field and you had an electron moving in it, then the electron would be deflected. So an electron would be deflected in such a way that it would go around this way. Now, a positive charged particle would go around that way, but electrons would go clockwise. Okay, because remember, right-hand rule. You put your hand in the direction of the velocity, curl your fingers in the direction of the magnetic field, your thumb points in the direction of the force, except electrons are negative, so they go the other way. Okay, so we're going to do cyclotron motion, and so what we're going to do is we're going to build a magnetron, which would be a small device in a vacuum in which you have a magnetic field, and you're going to have electrons injected into it at relatively high velocities. Okay, and so they're going to spin around. Okay, so you would build an evacuated chamber here, and you would have a coil, wire around here, create magnetic field, and then you shoot the electrons in there, and they'd start spinning. Okay, so we use a coil to produce a magnetic field. And so you remember that the coil is now going to be essentially a solenoid. So we know the magnetic field of the solenoid is mu naught N times I. All right. So if we assume that our coil has 320 turns, and we assume the length of the coil is 12 centimeters, then I want to know what current has to be in the coil so that the magnetic field in the coil is sufficient to give us the cyclotron motion that we would like to have. Okay, so what do we do? Well, let's remember back to cyclotron motion. So we know that the cyclotron frequency, okay, is going to be QB over 2 pi m. Now that's actually from page 815 of your textbook. So that's page 815 of your textbook right there. Okay, where magnitude of Q. So we're doing electrons, then this is going to be EB over 2 pi m. Okay, so there we have the basics right there. Okay, so the next thing we want to do is we say, okay, for the coil, okay, then we know that B equals mu naught N I. Okay, so if we plug that into the previous equation, then what we've got is we've got the frequency is Q. Well, the Q is the absolute value of the Q is going to be the fundamental charge, so that's going to be just E. Okay, and times mu naught N I. divided by, okay, I don't know why this stylus is doing, okay, so mu naught E mu naught Ni divided by 2 pi m. So we're trying to find I. Okay, so that's going to be 2 pi mf divided by E times mu naught times n. Okay. Okay. So there we have solving for I. Okay. And so all we have to do is figure this out. First step is n. Okay, so n is the number of turns over the length. And so what you would think is that this is going to be the number of turns, 320. Okay, and we're going to divide 320 by 12. Okay, so what's wrong with that? Because that's not right. Well, this is going to be in turns per length, so it'll be so many turns per length. What this gives me, the way I've written it, is turns per centimeter. So if you want this to be SI units instead of centimeters, this must be meters. So really, this is going to look like 320 divided by 0.12 meters. Okay, remember, units are important. I've been stressing that all semester. Units are very, very important. Okay, so if you plug that in like that, that gives you 2670. Okay. Now, what we can do is, now that we have that, we go back to our formula that we had derived for the current. So that's going to be 2 pi mf divided by E mu naught n. So that's now going to be 2 pi, mass of electron 9.11 times 10 to the minus 31 kilograms, times the frequency 750 megahertz, okay, divided by 1.602 times 10 to the minus 19 coulombs, 4 pi times 10 to the minus 7 Tesla meter per amp. Okay, and that's now 2670. And so that would tell us the current would be 7.99 amps. So we need 7.99 amps in that coil in order to produce that level of magnetic field that would make electrons injected into its spin at 750 megahertz.